Welcome back to our series on archived satellite data from the class server system. Previous MetPy Mondays, we've ordered data, retrieved data, and looked at the visible satellite imagery. Today what we're going to do is we're going to inspect the infrared channel 4 from our GOES 13 satellite data that we retrieved from our class server, and investigate how we can plot brightness temperature from that data. We're going to go ahead and start with a new Jupyter notebook this time. I've already got one open here, so go ahead and open a new one. But I've also opened up the one that we've been working on over the previous couple of MetPy Mondays, the visible satellite imagery, so we can maybe go back and forth and use a few of the cells, or at least copy and paste some of that information over to make less typing in the end. But first what we want to do is we want to go ahead and import a bunch of things so we can just have them to use throughout our notebook here. So we're going to import from CartoPy the coordinate reference system as CCRS. We're going to import CartoPy.feature as CFeature. We're going to import matplotlib.pyplot as PLT. We're going to import, or from netcdf4, we're going to import dataset and num2date. And we're going to import Numpy as NP. Let's go ahead and run that cell to import all of these different modules for our use throughout our Jupyter notebook. And so first things first, we're going to go ahead and set up a file name. So file_ir. Here again, I have saved off my data in a directory that is back1 directory from my current working directory in satellite data. Your data may be stored in a different location. And we want to go ahead and use our infrared file here. And we're going to specifically use our channel 4 data, which is the 10.7 micron data set. And so we're going to set up that variable name so we can use it. And then specifically we want to set up and bring in our data set using the dataset functionality from netcdf4. And we're going to bring in file_ir. And we're going to allow that to have read functionality. So now that we've gone ahead and brought this data in, we can go ahead and look at what is contained in here. And so we're going to list from our dataset_ir the variables. And so you see that if you remember from previous MetPy Mondays, this is actually the same exact list of variables that are available in our infrared file that are available in our visible file. And so again, what we want to do here is we want to be able to pull off the data. And again, our data, since this is in netcdf format, is going to be in that 16-bit format. And so when we bring it in, we're going to want to change that to our 10-bit format. So we're going to go ahead and save off ir_10-bit equals ds_ir dot variables data. We're going to want just the initial time since we only have one time in the file. And we're going to divide it by 32. This dividing by 32 is going to go ahead and shift it from 16-bit data to 10-bit data, which we're going to be able to use with other equations to then get ultimately to our brightness temperature. So we'll go ahead and run that. And now we've got our ir_10-bit variable name with our data from our file. Now it turns out that from our infrared data to our visible data, we have a change in the resolution. And so we have fewer numbers of lat long points, and so we need to go ahead and bring in our lat_ir here. And again, we're going to mask this data using the Numpy masked values functionality. And so we're going to bring in ds_ir.variables lat, and then all the data we want to bring in, so the colon, or the square bracket colon. And then we need our mask value. And that mask value is 2.14329 e to the plus 09. And we're going to go ahead and copy this again, because not only do we need to do this for our latitudes, but we need to do this for our longitudes as well, so we're just going to go through and make some couple quick changes here to our longitudes and bring in our masked values. Similarly, now we will also want to mask our IR data set, so we're going to go IR underscore masked equals np.ma.masked underscore array. And we want to mask the IR underscore 10-bit data set using our tab completion and set up our mask to be our lat underscore IR dot mask. And so there we have it. We're kind of back at the beginning here where we have our mask data for both our lats, lons, and our IR. But now we need to ask ourselves, well, how do we actually interpret this data? We have this 10-bit count data again, but we need brightness temperature. And so we need to go back to our Google machine, and we could either research for Go's calibration, or if you have that calibration file already up, the website here with our calibration. So if you're not here, you can search Go's calibration, get to the site. We've used a couple pieces from this site. For our visible data, we were looking at how to calibrate our visible channel, which was here. But now we want to learn how to convert our GVAR counts to temperatures for the infrared channels, which is the next to last bullet point under the initial Go's calibration setting. So let's go ahead and click on that. And what we find here is we've got two pieces again. We need to convert first our GVAR counts to our scene radiances, and then from our scene radiance to brightness temperature. And so we see our scene radiance equation has changed just a little bit from our visible. So we have R equals X minus B divided by M. X here again is going to be our GVAR count data in that 10-bit format. B and M are going to be coefficients that are based on the particular satellite images we have. So we're coming from GOES 13, and so we want table 1.2 here, which is GOES 12 and later satellites. And remember, we are ultimately working with channel 4 data right now, our typical infrared 10.7 micron channel. And so we have a value of M equals 5.2285 and B equals 15.6854. And so we want to copy these values and set up variables within our Jupyter Notebook. So let's go ahead and set up M underscore IR equals, and I copy and paste here the value of 5.2285. And we're going to copy the value for B. B underscore IR equals 15.6854. And so now using this data and using these values from that website, we can go ahead and calculate our scene radiance for the infrared imagery. And here we have that X, which is going to be IR underscore masked for us, minus B underscore IR, divided by M underscore IR. And we will now have our scene radiance once running that cell. And so now we have our scene radiance, but we're not quite to brightness temperature. And so coming back to our website here that contains how we convert from GVAR counts to brightness temperature, we need to move on to step 2. Step 2 has a 3-step process where we take our radiances. So step 1 was converting our GVAR counts to radiance, done. Now we want to convert radiance to effective temperature. And how we're going to do that is we're using an inverse Planck function as described here in this box. And so we're going to need to bring in these values of C1 and C2 inverse Planck constant values to then be able to use this effective temperature that we calculate into getting our brightness temperature, or the actual temperature in Kelvin, from our effective temperature. And so the first thing that we're going to do is we're going to go ahead and copy these values. So we're going to copy C1 equals, and we want to remember here that we have 10 to the minus 5th. And so when we come back to our Jupyter Notebook, we'll go ahead and paste that e to the minus 5. And we'll set up C2 equals. And then we want to copy this 1.438833 value. And let's go ahead and add in a comment here just to let us know here that these are the inverse Planck function constants. So we'll go ahead and run that. So now we have C1 and C2. But notice from our equation here that we have C2, C1, and R. We've got all those. But then we need this N value. The N value here, along with our constants A and B in converting our effective temperature to the brightness temperatures, are going to be unique to each satellite. And so we need to scroll down to find the appropriate table that contains these values. And so remember, we're using GOES 13 data, so we need to find table 2.6, which contains our GOES 13 imager coefficients. And we're looking at channel 4 here, and we're going to use detector A as default. And so we have values for N, A, and B that we want to save off. And so let's go ahead and copy here the value for N into our Jupyter notebook. N underscore IR equals 937.23. Our A value equals minus 0.386 and so on. Go ahead and copy that. A underscore IR equals that value. And then B underscore IR, go back and grab one more value here, 1.001298. Go ahead and copy and paste that value. And now we have all of our constants. We can go ahead and add back in here this value of GOES 13 coefficients for channel 4. And so now we're set up to calculate our brightness temperatures from our scene radiances. And so the first thing we need to do is to be able to put in our equation for the inverse Planck function to calculate the effective T underscore effective underscore IR. And recall here that it's C2 times N underscore IR divided by np.log, which is going to be our natural log, of 1 plus the quantity C1 times N to the third, that's N underscore IR to the third, divided by R underscore IR. So again here, this is our inverse Planck function, C2 times N underscore IR, divided by the log of 1 plus C1 times N underscore IR to the third power, divided by R underscore IR. And again, we get a little warning here because of an issue in the log. Again, we have some missing values in our data, and so that sometimes gives us these runtime warnings. Nothing to be concerned about there. And now to get to brightness temperature. Brightness temperature of our infrared equals our A underscore IR plus B underscore IR times this effective temperature, T underscore, and then hit tab for autocomplete. And then we can go ahead and print out BT underscore IR.max to see what our max brightness temperature value should be. And upon calculation, it's 331 Kelvin, which seems reasonable for a warm skin temperature of the ground. And so now we can go ahead and create a simple plot, of which now we're going to go back to our visible satellite data to go ahead and quickly create a simple plot. Go ahead and take this last one here, grabbing all of our data so we can go ahead and copy and paste this over. We're going to need to make a few changes here. We're going to get our time from DS underscore IR. And so we'll need to change that in 2 places. Set up our figure. Oops, we don't have a map projection in here yet, so we need to go ahead and set that up. So map CRS equals CCRS geostationary. And then we need to set up our central longitude, again, with minus 75. We're going to need to go ahead and find these lat-lon points again. And so we're going to have to come back over to our visible satellite data, scroll on back up to find where we set up our values here. And so we need to go ahead and first figure out our individual points. And garner our values. Now through all of these here, we've changed the name of Latin lawn. It's going to be lawn underscore IR. Lawn underscore IR. Copy, paste that again. Here we're going to have lat underscore IR. Go ahead and copy that and paste, and paste. Then the rest should be okay because now we've called them the same thing. And so that's going to get our set extent correct. But now we want to go ahead and do our brightness temperature underscore IR. Here we're not going to need to reverse our gray, so we can go ahead and delete that. We'll bring in our coastlines and then change this to infrared satellite imagery. And we'll go ahead and run it. It turns out that lawn is not defined here because we did miss one thing. To switch over these to lawn underscore IRs and our other variables here to lat underscore IRs. And lo and behold, there we get an infrared satellite imagery in our nice black and white version. In future MetPy Mondays, we're going to look at water vapor imagery and how we can modify this imagery to use color maps as well. Thanks for listening, and we'll see you next time.